Let's move on to the second conjugation property, which says x of t is imaginary. Okay, so what happens if x of t is imaginary? So we have already seen when we talked about continuous time Fourier series as what? When do we say a signal is imaginary here? It satisfies this condition. So what is that? X star of t should be equal to minus x of t. If any signal x of t satisfies this condition, which is x star of t equal to minus x of t, then we say that the corresponding signal x of t is an imaginary signal. Now let us see what happens in frequency domain. So just now we have seen that x star of t will have x star of minus j omega as the Fourier transform, and that should be equal to minus x of j omega. Okay, so in frequency domain it translates to x star of minus j omega equal to minus x of j omega. So what does this mean? This means that the corresponding Fourier transform is conjugate anti-symmetric. Okay, y x star of minus j omega is equal to minus x of j omega. So that corresponds to conjugate anti-symmetry property. So what does it mean? If the signal in time domain is imaginary, then its Fourier transform would be conjugate anti-symmetric. Okay, now let us try to write these things in terms of real and imaginary parts. Okay, so this because we have already done enough number of times, I am directly writing. We get xr of minus j omega minus j times xi of minus j omega, correct, is equal to minus xr of j omega minus j times xi of j omega. Okay, so x star of minus j omega we already got before. I am just replacing that here, and minus x of j omega implies minus xr of j omega minus j times xi of j omega. Now equating real and imaginary parts, what do you get? This implies xr of minus j omega would be equal to minus xr of j omega. So clearly what does it mean? It means that real part of the Fourier transform is odd. Okay, and also what do you see? You see that xi of minus j omega is equal to xi of j omega. So again, what does it mean? The imaginary part of the Fourier transform is even. Okay, so that much amount of information we get when the signal x of t is imaginary. So we can tell that if a signal x of t is imaginary, then its Fourier transform is conjugate antisymmetric, and the real part of the Fourier transform is odd, and imaginary part of the Fourier transform is even. Okay, right, so let's move to the third property, which says x of t is even. Okay, so x of t is even. So what does it mean? It means that x of minus t is same as x of t. Now this we already know. Okay, now if you go into frequency domain, which property we have to use here? Time reversal property. So we get x of minus j omega, correct? Fourier transform of x of minus t is x of minus j omega, and that should be equal to x of j omega. Clearly what does this mean? X of minus j omega equal to x of j omega. That implies the Fourier transform is also even. So if the signal is even, then Fourier transform is also even. So just for understanding, we'll take a small example. You remember the third example which we have seen, which is e power minus a mod t with a greater than 0. So what is this fellow's Fourier transform? That we got it to be x of j omega, which is equal to 2a by a square plus omega square, correct? So what happened? Note that this signal is real and this fellow is even. Why? X of minus t would be equal to how much here? e power minus a modulus of minus t, which is same as e power minus a modulus of t, means this fellow is even. Now let us see what happens in frequency domain. X of minus j omega would be equal to again 2a by a squared plus minus omega whole square, which would be equal to 2a by a square plus omega square, which is equal to x of j omega, and hence what did we get? We get x of minus j omega to be x of j omega, and hence the Fourier transform is also even. Okay, so it means what? If the signal is even, then the Fourier transform is also even. Okay, right. Now you can take one more example. Let us take rectangular function, right? So if you take the Fourier the signal to be a rectangular function from -1 to +1 with amplitude 1, is this even? Yes. So definitely what happens, the Fourier transform, we know that to be how much? 2 sine omega, capital T is 1, and hence you get 2 sine omega by omega. So clearly you can see that x of t is even, and Fourier transform x of j omega is also even. Why? If you replace omega with minus omega, you will get again 2 sine of minus omega by minus omega, which is same as 2 sine omega by omega. So if the signal is even, then the Fourier transform is also even. Okay. Next, we'll take the fourth property, which is x of t is odd. Okay, so this again, what happens when do you say signal is odd? Yeah, if you say signal is odd, if it satisfies this property, what is that? X of minus t should be equal to minus x of t. Now if you go into frequency domain and using time reversal property, x of minus t will have x of minus j omega, which is equal to minus x of j omega. Okay, yes, so x of minus t equal to minus x of t means what? The signal is odd. X of minus j omega equal to minus x of j omega means Fourier transform is also odd. So if the signal is odd, then the Fourier transform is also odd. Okay. Yes, we will take a small example. So if you remember, I mean fourth signal. Okay, let us take fourth example. X of t to be e power minus a t u of t minus e power a t u of minus t. Correct. So if you plot this function, it looks like this. We have seen this already. Okay, this one. Correct. So the plot of the signal will look like this. So clearly you can see that this is an odd signal. Why? We can prove that x of minus t means what? You rotate the signal along y-axis by 180 degrees and multiply with -1. So if you multiply with -1, you will get back the signal. So clearly the signal is odd. So what happens to this Fourier transform? X of j omega, we got that to be how much? Minus 2j omega divided by a squared plus omega squared. So now let us see what property it satisfies. So x of minus j omega would be equal to how much? Yeah, that should be equal to plus 2j omega by a squared plus omega squared. Okay, why? You replace omega with minus omega, you'll get 2j omega by a square plus again minus omega whole square. Okay, so that we can that can be written as minus x of, or what I'll do, I'll multiply this with -1. So minus x of minus j omega would be equal to how much here? Minus x of minus j omega would be minus 2j omega by a square plus omega square. So clearly this is equal to x of j omega. Means what? We got minus x of minus j omega equal to x of j omega. Means what? The Fourier transform is odd. So if the signal is odd, then the Fourier transform is also odd. Okay.